All right, so we are getting into section 6.3, which is about modeling with polynomial functions. We've talked about polynomial functions in general, just in terms of math. So we've talked about linear and quadratic and cubic functions and some other behaviors. But now it's time to actually start applying these to problems. Let's take a quick look over at the type of candidate models that we have to model different data behavior. So for increasing at a constant rate data, we have a linear model. For increasing at and I can actually, let's draw a little picture. Increasing at a constant rate, that looks like that. Increasing at an increasing rate looks like that. So exponential and polynomial could model this depending on, with polynomial modeling, you have kind of, it can be very accurate over certain portions and not over others, so it could go up and down and so forth. Increasing at a decreasing rate looks like this. So that could be logarithmic or polynomial. Decreasing at a constant rate, that's linear. Decreasing at an increasing rate, the only one we have for that is polynomial modeling, and decreasing at a decreasing rate, like so. That could be one of three things: exponential, logarithmic, or polynomial. So to describe all these different kinds of behavior, we have these candidate models. A thing that we have to kind of confront in terms of polynomial modeling is we don't have the same sorts of metrics that we had for some of our other models, specifically the correlation coefficient. If we are looking at nonlinear polynomial regression, so that means any kind of regression that's higher than lines, so quadratic, cubic, and quartic, then these actually don't have a correlation coefficient. And the reason for that involves the mathematics behind the actual regressions. So instead of the correlation coefficient, we have another measure which is called the coefficient of determination. And the symbol for that is capital R squared. That's capital R squared. And that's to measure the goodness of fit. So if you have a regression that does have a correlation coefficient, for example, linear, exponential, logarithmic, any of the ones that we've done up to this point, then to get its coefficient of determination, we simply square the correlation coefficient. So it's a little bit confusing, but so for anything that has a correlation coefficient, we get this thing called the coefficient of determination by squaring the correlation coefficient. If it is one of these special types of regression, quadratic, cubic, or quartic polynomial regression, then we don't have a correlation coefficient, and so we have the coefficient of determination, which of course leads you to the question, how do you find this if you don't have the correlation coefficient? Well, the way you find it is by going to your calculator, and I'll show you how in just a moment. It's very easy. But to a little bit more about this coefficient of determination, it's a number that's always between 0 and 1, so it's similar to the correlation coefficient in that regard. And if you multiply it by 100, so you put it in percent form, then it measures the percent of variation in the data that's explained by the regression model. And so that's a useful thing to have at our disposal. How much variation is explained by the regression model? Okay. Let's get into actually modeling something, and then we can find the coefficient of determination. Okay, so what we have here is data from 1900 to 1990. This is for the Western U.S. And population data every 10 years in millions. And so what I'm going to do is I want to model this data with some of our various models that we have already, like exponential and so forth. And since this is kind of a big data set, I'm not going to actually do this. I'm just going to run through the slides, and then I'll probably actually model just some of it. But so here's our data. And let's begin with an exponential model. So, the way you would do this is you'd enter this as L1. This would be L2. And then we would just do xbreg for all of these points. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 values. And, oops, going the wrong way. If you do your exponential regression, you will get this function. Now we're also going to be interested in the SSE and the correlation coefficient and so forth. So, to find the SSE, the process is the same as it's always been. We do sum resid squared. The average error, we do the same thing. We take the square root of the SSE divided by 10. And then, now down here, what's actually happening here, because this is exponential regression, so it has a correlation coefficient. So the process is just to find our, actually maybe I'll just run through this very quickly on the calculator. Okay, so as I was saying, I went ahead and entered this data in on the calculator, and I'm going to go ahead and find the exponential regression for this. And then I want to calculate the coefficient of determination. So here's where it is. But now since this is exponential regression, it has a correlation coefficient. So you go to statistics, VARS statistics, equation, and you see here number 7 is R, that's your correlation coefficient. Then number 8 is little r squared. That's actually what we want for the exponential regression. Now I want to show you, just so you don't get confused, there's also a big R squared, and for anything that doesn't have a correlation coefficient, this is what we use for the coefficient of determination. So that's a bit confusing, but that's the way it is. So R squared is 0.99023, and that is our coefficient of determination. Now we could graph this, and one thing to notice is that you've got a slight overprediction here at 90. So now we're basically just going to do this again for the other types of regressions. So we're going to do this for a quadratic, and I'll just show you where this is located. So you would go to Stat Calc, and then you see number 5 is quadreg. So it's very easy. Of course I messed something up. What did I mess up? I did not put a comma. Okay, let's try that again. There's our quadratic regression, and to get its coefficient of determination, again we go to VARS statistics, equation, but this time we're going to go to the big R squared, capital R, because it's quadratic, which does not have a correlation coefficient. And that's 0.997576, I guess. And that's where this number comes from. Okay, so if you graph this, you'll see a slightly better fit. We could do this again for the cubic model. And once again, cubic regression is located under Stat Calc. That's number 6, cubic. And notice also underneath it is number 7, that's quartic, that's 4th degree. So this is 2nd degree polynomial, 3rd degree polynomial, and 4th degree polynomial regression right here. So for any of those 3. And also those are the 3 that we have to find the big R squared for the coefficient determination. Now if you did the cubic regression, you get these values in this function. I just want to point out that for the A coefficient, that this number right here is actually 0.0001488. That's 1, 2, 3, 4, 5. That's this e to the negative 5. It's scientific notation, so this is actually a very small number. And if you found its coefficient of determination, you'd get this value. Okay, its SSE is 5.222, and you calculate those in the same way. And then we could repeat this process for the quartic regression. And once again, we have 2 very small coefficients there. And we find the SSE, the average error, and the coefficient of determination in exactly the same fashion as we did for the cubic and the quadratic. Okay, so comparing all of these models, and I know that we haven't actually done every one of these steps, but I think that you can understand kind of what all this data means at this point. The SSE for the quartic is the best, is the smallest of all of them, and also the average error is the smallest, as you would expect. Also, the coefficient of determination is the largest, the closest to 1 of the 4 models. So the quartic is at least at first glance seems to be the best choice for our regression model. Okay. Now let's dig a little deeper into this. So as I said, the quartic model best fits the data. We know, it has the smallest SSE and average error, and it has the coefficient of determination that's closest to 1. But here's the problem. So over this data set, over the given 1900 to 1990 data set, it's a very good fit. But we know that this quartic model it behaves like a quartic. It has turning points. And this one has a negative leading coefficient, by the way. Let me go back to that. So it's negative. Its highest power coefficient is negative, which means that it looks like that. So basically what's happening here is that we've got great modeling over this area right here, but as time passes and you go outside of the data set, we have a turning point which comes shooting back downwards. And as we know, this is the population of the U.S. This is not accurate. Like this is 1990. So from 1990 up to 2020, we have not crested and then gone precipitously downwards, right? So even though the quartic model does a great job of following the data over the data set, outside of the data set it does not do a good job. And in fact, the cubic is better. Cubics kind of look like this, and that is a better fit in the long run than the quartic. So that's the kind of tricky thing about modeling, is that even though these numbers that we've got at this point might indicate one choice, the presence of turning points can complicate matters. Okay. So we should use the cubic model for this, and there it is as our best regression, best fit to the data. Because, well, I guess really what I should say is it's not only the best fit to the data, but it's the best fit to the data and to the overall trend. It doesn't have the turning points. Okay. So we can answer some questions about this cubic model. So let's talk about this average error in relative terms and what we can conclude about the fit from the correlation coefficient and the coefficient of determination.